Hello, my amazing students. This is Mrs. A here in our little vacation home. Everyone else just left for the pool except for a few stragglers who are underage. And I'm about to do your 8.1, 2, and 3 videos, or as much as I can get done while everybody's out of the house. So I hope that you enjoy and use these videos. Remember, I will be able to recap the big concepts here, but I will not have time to go over these entire video slides for you. So you need to do what you can in my absence using these PowerPoints and the videos for 8.1, 8.2, 8.3. The big concept that I want you to realize as we go through this is, remember, in 7.1, 7.2, we basically talked about confidence intervals, and then we went through confidence intervals for proportions and confidence intervals for means. And when we got to means, we talked about both small and large, and we'll talk about that too today. So here it goes. All right, so here we are starting 8.1, and 8.1 is all about the basics of hypothesis testing. So notice that we're going to talk about just the basic overall general hypothesis testing first, and then we're going to talk about testing a claim about a proportion, just like we did in 7.1, and we're going to talk about testing a claim about a mean, just like we did in 7.2. And then we are not going to worry about this 8.4. That's not part of our class. So a hypothesis is a claim or a statement about a property of a population or a population parameter. Okay, so a hypothesis test is a procedure for testing a claim about a property of a population or a population parameter. An automobile manufacturer advertises that its new hybrid car has a mean mileage of 50 miles per gallon. To test this claim, a sample would be taken. If the sample mean differs enough from the advertised mean, you can decide that the advertisement is wrong. Okay, so testing a hypothesis, you're going to need a pair of hypotheses. One that represents the claim, and the other is its complement. When one of these hypotheses is false, the other must be true. And so we're going to talk about what is a null hypothesis. The null hypothesis always has an equal portion in it. So it is a statistical hypothesis that contains a statement of equality such as less than or equal to, or greater than or equal to. Okay, we always call the null hypothesis H sub O or H sub naught. Okay, so null, H sub naught, H sub 0, and the alternative hypothesis is going to be the complement of that null hypothesis, and it is not going to have an equality in it. It is a statement of strict inequality, such as greater than, not equal to, or less than. Must be true if H sub naught is false. It's denoted by H sub A, and they are complementary statements. So if one is true, the other one is not true, and vice versa. Okay, so stating a hypothesis, to write the null and alternative hypotheses, translate the claim made about the population parameter from a verbal statement to a mathematical statement. Then write its complement. So if the H sub O is the mean is less than or equal to K, then the H sub A, the alternative hypothesis, must be the mean is greater than K, because together they take care of every eventuality. Okay, so if the H sub O is the mean is greater than or equal to K, then the H sub A is the mean is less than K. And the last one is equal to and not equal to. Okay, so regardless of which pair of hypotheses you use, you always assume that the mean equals the K. In other words, you're going to examine the distribution on the basis of this assumption. We're always going to assume that the H sub O is the true statement. Write the claim as a mathematical sentence. State the null and alternative hypotheses and identify which represents the claim. A school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. So they're claiming that this proportion is 61%. So we want an equal sign there. So the H sub O is the percentage, or the proportion is equal to 0.61. And the H sub A is that it's not equal to 0.61. Now we have to be very careful. The first time I did this problem, I saw this at least 1. And I thought, oh, it's greater than or equal to. But then I realized that the is, they're saying the proportion of students who are, and then they're qualifying the students they're talking about, not their statement of equality here. So the proportion is 61. So we need an equal sign and a not equal sign. And the claim that the school is claiming is the H sub O. We always make the H sub O the one with the equal sign. We always make the H sub A the one without the equal sign. But the claim can actually be either one, depending on the situation. Okay, write the claim as a mathematical sentence. State the null and alternative hypotheses and identify which represents the claim. A car dealership announces that the mean time for an oil change is less than 15 minutes. So since they didn't say less than or equal to, we're going to have an alternative that says mu is less than 15. So that means our H sub 0 will be mu is greater than or equal to. Okay, so this one is the claim. The H sub A is the claim. But the H sub O is the one that has to have the equal sign in it. A company advertises that the mean life of its furnaces is more than 18 years. So more than is greater than. So that will be our H sub A, but our claim is not our H sub A, okay? So we have our H sub A is the mean is greater than 18, and the H sub O has to have the equal sign in it, so it will be the complement, less than or equal to 18, and the claim is the H sub A. All right, so here's some just other examples that I wanted to show you. Remember that I put a whole bunch of examples in your PowerPoints. So there's a 10.1 and a 10.2 and a 10.3 that are just more examples of writing down the hypotheses. Okay, so that's just a lot of practice for you to go through the PowerPoints. So now we're going to talk about the procedure involved in the hypothesis test. So let me see if I can get just a little bit closer to this and give you a better screenshot here. Okay, so on the first one, it says identify the claim. Identify the claim to be tested and express it in symbolic form. Number 2, give the symbolic form. Identify the null and alternative hypotheses, which we just practiced. Number 4 is select the significance level. Select the significance level alpha based on the seriousness of a type 1 error. Make alpha small if the consequences of rejecting a true H sub 0 are severe. These are common values for your significance level. Okay, so now let's move down a little bit. And step 5. Identify the test statistic. Okay, the test statistic is going to be either the P or the proportion, which can also be a percentage, or it might be the mean. And so basically, then we're going to talk about what is the appropriate sampling distribution. Are we going to use the normal distribution or the t distribution? Now this chi-square is outside the range of this class, so you don't have to worry about the chi-square. We don't use it in this course. It's a little bit more complicated and saved for higher statistics classes than our standard intro course. Okay, so now let's look at number 6. We have 2 different methods. We're going to explore each method. We're going to find the values. In the p-value method, we're going to find the p-value. So we're going to find the value of the test statistic and the p-value. And then we're going to draw a graph that shows the test statistic and the p-value. Okay, if we're using the critical value method, we're going to find the value of the test statistic and the critical values. Then we're going to draw a graph showing the test statistic and the critical values and the critical region. So we have 2 different decision paradigms here that we're going to practice each one. And then number 7, we're going to make a decision. We're going to either reject H sub O, or we're going to fail to reject. So if we're talking about the p-values here, okay, on the left, we're going to reject H sub O if the p-value is less than or equal to the alpha. We're going to fail to reject H sub O if the p-value is greater than the alpha. Over here on the critical value method, we're going to reject H sub O if the test statistic is in the critical region. And we're going to fail to reject the H sub O if the test statistic is not in the critical region. And then lastly, at the very end, we're going to spend some time working on this also. Restate the previous decision in simple, non-technical terms and address the original claim. And they have some very specific ways that they want us to do that. But that's generally the simple process that we're going to be doing over and over again. Remember, we're going to be looking at several different scenarios, whether we're talking about a population or a mean of a small sample, mean of a large sample, but just the same type of situations we were using before when we did our confidence intervals. So it's very much the same, and you're going to see how closely it follows. So now when we're talking about the confidence interval method, you have these in your book. Okay, so construct a confidence interval with a confidence level selected. We did this in 7.1 and 2. This is the same confidence interval here because a confidence interval estimate of a population parameter contains the likely values of that parameter. Reject any claim that the population parameter has a value that is not included in the confidence interval. In other words, the confidence interval is always reasonable values for our parameter that we're looking for. Okay, so if the one that we're trying to test is outside that confidence level, then we can reject it. Okay, confidence level for a confidence interval is significance 0.01, and then 0.025, and then 0.10, and this was 2-tailed and 1-tailed test. So those are just some confidence levels that you can use when you want to do that. But in the big picture, this chapter is not about confidence intervals. This chapter is about hypothesis tests. So I really don't want you to put a whole bunch of emphasis on this one. Kind of just brush over it. We're really not going to stress this in our class. So here are the general steps for hypothesis testing. Okay, so in step 1, we're going to state the claim mathematically and verbally. We're going to give it in symbolic form. We're going to identify the null and alternative hypotheses. The H sub O, what does that equal? The H sub A, what does that equal? We're going to specify the level of significance, which is usually stated in our problem. But if they don't give it to us, we will often use 0.05 because 0.05 is very often used as a default setting for the level of significance. We're going to determine the standardized sampling distribution, and we're going to sketch its graph. We're going to identify the test statistic. We're going to calculate the value of the test statistic and the p-value. Uh-oh, I left an L out of there. Or the critical value. Add it to your sketch. So basically, when we're looking at number 5, we're going to be saying, okay, do I use the Z or the T? okay? And when I come over here and I calculate my test statistic, I'm going to say, is my test statistic in this rejection region? So we're going to talk about how to make those decisions very shortly. Then the next page is how we make our decision. We're going to make a decision using the following decision rules. If we're using a p-value, we're going to say, is our p-value less than or equal to the level of significance, alpha? Or if we're using a critical region, is the test statistic in the critical region? If we can say yes to those, then we reject the H sub 0. If we can say no to each one of those, or one or the other, we fail to reject the H sub O. Then lastly, we write a statement to interpret the decision in the context of the original claim. Now what I've just done here is just a restatement. Okay, let's go back. A restatement of this. So basically, this one was the one that was provided in your textbook, and this is the one that I had from old PowerPoint slides that I liked a lot. So I put them both in there. They're both the same material. Okay, so use the original claim to create a null H sub O and an alternative hypothesis H sub A. So now this is from your book, and we're breaking down each one of these steps. Identify the claim, okay, give it in symbolic form, and then write your H sub O and H sub A. We've already practiced that, okay? Step 4 is the significance level. Alpha is the same alpha that we introduced in the section 7.1 where we defined the critical value. Common choices, 0.05, 0.01, 0.10. 0.05 is the most common. So the significance level alpha for a hypothesis test is the probability value used as the cutoff for determining when the sample evidence constitutes significant evidence against the null hypothesis. By its nature, the significance level alpha is the probability of mistakenly rejecting the null hypothesis when it is true. Okay, so alpha is the probability of rejecting the null hypothesis when it is actually true. So that we're going to talk about the different types of errors that you can have, and that is one type of error, rejecting H sub 0 when H sub 0 is really true. Okay, so the level of significance, we're going to, when you're looking at what is the level of significance, it's your maximum allowable probability of making a type 1 error, okay, and it's denoted by alpha. And by setting the level of significance at a small value, you are saying that you want the probability of rejecting a true null hypothesis to be small. So those are the common ones. Again, this is a restatement of the last slide. And then the probability of a type 2 error is a beta, and beta is 1 minus alpha. Okay, so if we look, we want a small beta, then we're going to make alpha larger. If we want a small alpha, we make the beta larger. Okay, a small alpha reduces the risk of a type 1 error. However, there's a drawback. If we reduce the alpha, we also increase the probability of a type 2 error. So we're going to have more about errors a little bit later in the PowerPoint. So this is step 5 of, and this is again equivalent to each one of the slides you've seen before. So identify the test statistic that is relevant to the test and determine its sampling distribution. Are we going to use the normal? Are we going to use the t-distribution? The rules here are the same rules that we used in the last section. Okay, so if we're doing a proportion test, we're going to use the standard normal. Our requirement is going to be that n times p is greater than or equal to 5 and n times q is greater than or equal to 5. And here is our test statistic. So this is a very good reference chart. If we're doing a mean test and we have, these are met, we're going to say we do not know the sigma, and it is normally distributed, then we would use a t-test. We do not know the sigma and the n is greater than 30, then we can use the t-test. The big deal is we use the t-test when we do not have a standard deviation, okay? So then when we're looking for the mean, we can use the normal z-score table, the standard normal table, if our sigma is known. Our standard deviation of the population. Again, remember, this is much more rare that we would not know the mean, but we would know the standard deviation. That's just weird. But occasionally they will give us that situation, and we can also use the z-score if we have a very large n and normal distribution, okay? And we'll see that on another slide somewhere. So there's the z-score test statistic. This one down here, we're not going to use at all because that's dealing with 8.4, which we don't cover in this slide, okay? So the next step is step 6. We're going to find the value of the test statistic and the p-value or the critical values. So if we're doing p-value, critical value, remember the little slide went down on 2 different decision paradigms there. So find the value of the test statistic and the p-value, or the test statistic and the critical values, and we'll talk more about those. Remember, this is your overview of all of hypothesis testing. The test statistic is a value used in making a decision about a null hypothesis. It is found by converting the sample statistics such as p-hat, x-bar, or s to a score such as z or t, with the assumption that the null hypothesis is true. Okay, so it is the score having to do with our data. The test statistic is our data score. Okay, and then the critical region is going to be determined by the critical region or rejection region is the area corresponding to all the values of the test statistic that cause us to reject the null hypothesis. This is going to have to do with our alpha, okay, with the level of surety that we need that we don't make a type 1 error. In a hypothesis test, the critical values separate the critical region where we reject the null hypothesis from the values of the test statistic that do not lead to rejection. So we have 3 types of hypothesis test, right? We have a left-tailed test, a right-tailed test, and a two-tailed test. And we're going to have to learn when we're going to use each one of these. Okay, the type of test depends on the region of the sampling distribution that favors a rejection of H sub O. Okay, so the test here is going to be determined by our H sub A. So if our H sub A is less than, we'll have a left-tailed test. If our H sub A is greater than, we'll have a right-tailed test. If our H sub A is not equal to, we'll have a two-tailed test. Okay, this region is indicated by the alternative hypothesis. So here we have each one of these, okay? The sign used in the, now H sub 1 here, it should be H sub A. I don't know why these translated to ones, but H sub A is not equal to, we have a two-tailed test. H sub A is less than, we have a left-tailed test. H sub A is greater than, and we have a right-tailed test. So here we have the alternative hypothesis contains less than equal. So here's our alternative, and you can think of that as a little arrow pointing to the left, so we have a left-tailed test. Okay, and our test statistic will be dividing this region here. Our critical value will divide this, and then we have to decide whether our critical value is inside or outside, whether our test statistic is to the left or to the right. Now the standardized test statistic is actually our critical value. So what they mean by test statistic here is our standardized test statistic, which is going to be our Z sub C. So P is the area to the left of the standardized statistic here. It's also called your rejection region. A right-tailed test, you see our mean is greater than K for our alternative hypothesis. So we have a right-tailed test. And our standardized test statistic is here. And then the area to the right of it will be our rejection region. And then when we have a not equal to, we're going to have a two-tailed test. So here we have split our alpha into two parts. Okay, so we split the alpha in half. Each tail has an area of 1/2 P. Okay, P is twice the area to the right. Okay, so we're going to talk about when do we double the P, and we only double the P value when we are having a two-tailed test, and we'll see more of that later. So here we have an example, identifying the nature of the test. Let's see a little bit more on the screen here. Okay, somehow I lost that. Sorry about that. Okay, for each claim, state H sub O and H sub A, and then determine whether the hypothesis test is left-tailed, right-tailed, or two-tailed. Sketch a normal sampling distribution and shade the area for the p-value. So here we have a school publicizes that the proportion of its students who are involved in at least one extracurricular activity is 61%. So our H sub O was equal to, that means our H sub A is not equal to, and this is going to be a two-tailed test. Okay, so two-tailed, and there they are. So the p-value is the part that corresponds to the alpha value, so 1/2 of it will be in this tail, 1/2 of it will be in this tail, and we have to double that p-value to compare it to the alpha, which we'll talk about later. For each claim, state H sub 0 and H sub A. Okay, car dealership announces that the mean time for an oil change is less than 15 minutes. So the H sub A is less than, therefore we have a left-tailed test. And there's the p-value area there. Okay, so then a company advertises that the mean life of its furnaces is more than 18 years. So more than is going to be a right-tailed test. There you have it. So how do we figure out what a p-value is? So we've got, remember, we got a p-value decision paradigm, and we've got a critical value and a critical region decision-making paradigm. So we have two things that we have to learn, and we can use one or the other. Sometimes we even choose to use both in the same problem just to verify. The probability, if the null hypothesis is true, of obtaining a sample statistic with a value as extreme or more extreme than the one determined from the sample data. Okay, so don't confuse the p-value with the parameter p or the statistic p hat. Know the following notation. The p-value is the probability of a test statistic at least as extreme as the one obtained. The p is the population proportion, and the p hat is the sample proportion. Okay, so rule on when to double the p-value. We only double the p-value when we are comparing two-tailed tests. Piggies with two tails are double the trouble. Always double the p-value before you compare with the sigma value in a two-tailed test. Never any other time. Compare the doubled p-value with entire alpha value before we split it in half to accommodate both tails. So that's how we're going to do a p-value test, is compare the p-value with the alpha. And the p-value depends on the nature of the test. The p-value is also going to depend on the alpha value that we're using. Okay, it will be the probability associated with the z-score on the standard normal table most often. So how do we find p-values? Okay, so up here, p-values, what type of test? Are we doing a left-tailed test or a right-tailed test, or are we going to do the, is the test statistic to the left or the right of the center. Okay, so here the left, if we're doing a left-tailed test, the p-value is the area to the left of the test statistic. If we're doing a right-tailed test, the p-value is the area to the right of the test statistic. Okay, and then it says, is the test statistic to the right or the left of the center? So here we've got p-value is twice this area because we have